guys, so we're here with a summary of basically all the intermolecular forces we talked about. So once again, intermolecular forces is basically holding, right, these molecules together. That's all they are, okay? And this is how we're thinking, adding that new layer to things we've already talked about before, but right, with solid, liquid, and gases. But now we're thinking of them on a molecular level as far as how those molecules are interacting with. Okay, so let's start out with the very first one, dispersion forces. Once again, this is a type of intermolecular force, and you're going to see dispersion or London forces in all molecules and atoms. Okay, so every single molecule can have this type of intermolecular force. And if we think about it, this is basically what's happening with London dispersion forces. A temporary dipole moment will occur, having our electrons on one end, no electrons on the other end, and we're going to see an interaction between my positive partial end interacting with my negative uh, partial end. Okay, so this is where our dispersion intermolecular forces occur. And then the key thing we want to understand with London forces is that these are the weakest intermolecular forces. Okay, so these are the weakest with the strength around 0.05 to around 20 kilojoules per mole. Okay, so the weakest force, all right, that's the key thing you just want to understand. These are the weakest force. And remember that these are temporary, so they're not permanent. They're not permanent. Just one note about dispersion forces, just to let everybody know, even though they are the weakest, there are times where they can be the strongest. Okay, and the only time we see this is when we have a super high molar mass. Okay, so you have a high molar mass, it is possible that the dispersion forces um, can be the strongest force. All right, but most of the time, dispersion forces are the weakest. Okay. Next, we got dipole dipole. Okay, so dipole dipole, dipole dipole, dipole dipole. All right, so dipole dipole forces. Man, you just gotta say that 3 times. It's crazy. But dipole dipole forces are only going to be present in polar molecules. Okay, only in polar molecules. So once again, you got to know what a polar molecule is in order to have dipole dipole forces. So if you need to make sure you review polar molecules. But polar molecules are the only ones that are going to have these dipole dipole forces. Okay. Yeah, so this polar molecule, we know polar molecules have a dipole moment. Specifically, they have a permanent dipole moment. So you do not want to confuse this with the dispersion, okay? All right, so they have this permanent dipole occurring. So we're going to have our positive end and our negative end, okay? And we're going to see this interaction between the two here, okay? My negative end being attracted to my positive end. And if we think about the strength, right, dipole dipoles are right after dispersion forces. Okay, so they're a little stronger than dispersion forces. Next up, we got hydrogen bonding. So hydrogen bonding, we're only going to see this first off occur, and the molecules must have hydrogen. So that's a key thing here. You got to have hydrogen, but also the hydrogen must be bound to either nitrogen, oxygen, or fluorine, NOF. Okay, so we're only going to see hydrogen bonding for those particular conditions. Right, so we look at this molecule here, this example of hydrogen bonding, right, where we got our hydrogen and our hydrogens here and oxygen. So we're going to see this negative end and our positive end. And our positive end, like, notice all these are the same. There's a partial positive and a partial negative, okay? So, but they're attracted to each other, intermolecular forces. So, right, my positive end will be attracted to my negative end. And this is where we see this hydrogen bonding start to occur. And hydrogen bonding is the strongest intermolecular force of my dipole and dispersion forces. Okay. Now, hydrogen bonding is the strongest, and it's the strongest when we're just thinking of pure compounds, per elements. However, we did talk about one other type of bond, ion dipole forces. And the key difference here is that this is where we have to evolve ions. Okay, so because we have ions here, it's going to be a way stronger type of attraction between the two. Okay, and with this being said, we're only going to see this with a mixture. So this is key. It's a mixture of ionic compounds. So you got to have an ionic compound, right? But also you need polar compounds. Okay, so those polar compounds have those permanent dipole moments, and they're attractive to those ionic compounds. So for instance, say we got a cation, the cation would be attracted to the partial negative ends. Okay, and this is where we see our ion dipole forces. And because of this, we have a very strong interaction, as this being the strongest of them all. So now that we know all the forces, let's look to example, right? And let's look at this. Which substance has the highest boiling point? Okay. So one thing we talked about is that, right, the higher the molar mass, the higher the boiling point, and that works for dispersion forces. But another trend that we have here is the stronger, right? The stronger, I can't keep saying this, the stronger the intermolecular force, the higher the boiling point. So you got to break this down. Which of these will have the highest boiling point? A key hint here is which one has the strongest intermolecular force. Okay, so we got A with CH3OH, we got B with CO, and then we got C with N2. So think about which, right? What is A, B, and C? What are those intermolecular forces? And then depending on that, you can then determine which one will have the highest boiling point.